let's get started with the one section from chapter 11 that we kind of started, but it was towards the end of class. There were some questions, so we're going to restart it. The last section is on buffers. A buffered solution is a solution that maintains a pH by neutralizing small amounts of added acid or base. If you were to add acid or base to just plain water, you would see drastic changes in the pH. You add a little bit of acid, the pH would drop way down to like 4. You add a little bit of base, it would rise up really high to like 10. That's just plain water. In a buffered solution, however, if you add a little bit of acid or a little bit of base, your pH is going to be about the same. So buffers resist changes in pH. And in our bodies, that's really important because we eat foods that will release acid or hydroxide, things that will change the pH of body fluids and things like that. And we also have a lot of cellular processes that go on that require a specific pH. And those processes also release acid and things like that that need to be dealt with. So buffers are very important for biological systems. So they're important for the functioning of cells and for blood. Your blood has a pH close to about 7.4. There's a very tight range that the pH of your blood needs to be in. And we'll talk about the buffering system in your blood at the end of this section. So is everybody clear on what a buffer is and kind of what it does? Okay. So what's in a buffer? Well, a buffer solution has a combination of an acid and a conjugate base. So we're looking at a weak acid and a salt of its conjugate base. The acid that we have here is acetic acid. That's what vinegar is. And then this acetate ion is the conjugate base. To remind you about what that means, the conjugate base, I'm going to write out the dissociation equation for you. So if we have aqueous acetic acid and we've got water around because it's aqueous, we're going to have a little bit of dissociation. Which means we're going to lose the hydrogen. And actually, I have a better way to show you this. The acid, which is the acetic acid, loses a hydrogen. We also call this donating a hydrogen. Same thing. It gives it up to the water. When that happens, the water now has an extra hydrogen. That makes it a conjugate acid. So the things on the product side are the conjugate acid and conjugate base. When that acid loses its hydrogen, it becomes the conjugate base, which is the acetate ion. Is that a little bit more clear? Because that was one of the things that I know we were a little bit fuzzy on. So let's say we wanted to make a buffer with acetic acid, which is the buffer. So the buffer solution would have acetic acid, and it would also have the salt, which we're getting to what the contents of the buffer would be on this slide. So give me 1 second, we'll go through that. So let's say we want to make a buffer with acetic acid. We'd have to have acetic acid, and then we'd have to have a salt that's going to give us the acetate ion. One example of that would be sodium acetate. That is an ionic compound, and when you put it in water, you get acetate and sodium ions. And you add the salt so that you have a higher concentration of conjugate base. So you have a large amount of your acid and a large amount of your conjugate base. And that's what makes up your buffer. So I'll write that out for you. Remember that we're dealing with a weak acid for a buffer. Does that answer your question, Deirdre? Good. So when we have this weak acid in a buffer, we've got some chemistry going on. Let's say that we've got this buffer that has acetic acid, lots of it, and it's got a lot of the acetate ion, which is the conjugate base. To this buffer, we add a little bit of base. So base is something that is going to have like an OH minus, okay? We need to look at the equation that we have for the acid, for the buffer, and see which way the equilibrium is going to be shifted. If we add base, this is a base, then that means we're going to shift towards making more of the conjugate base. Now we'll still have a little bit of this going on, right? Because remember, these are in equilibrium. But if you add a little bit of base, it's going to interact with the acid. So you can see that with the bars here, you start out with, let's say, equal amounts of weak acid and conjugate base. You add in a base, and that base will interact with the weak acid. So you lose a little bit of the weak acid, and you make a little bit extra of the conjugate base. But your pH is still maintained. Does that make sense? Okay. So now we got to talk about the opposite, right? So let's say that we have a small amount of acid added. When we add acid, that means that we're going to interact with the conjugate base. And when that happens, you're going to make more weak acid. We have to differentiate between the added acid and the weak acid. The weak acid is the one that's part of the buffer. The added acid is what the buffer is buffering against, okay? So we're going to shift the equilibrium towards making more of that weak acid, which in our case is acetic acid. So you can see it's still in equilibrium. It's just that things are shifted towards making more of the acetic acid in this case. So you'll need to differentiate between these two cases. This is what happens for any buffer, regardless of its contents, whether it's acetic acid, formic acid, or any other weak acid, plus its salt. This is what happens. Are we good? Yes, Jordan, what's your question? So you need to be able to differentiate between what happens when you add acid to a buffer and what happens when you add base. So are you making more conjugate acid or conjugate base, or are you making more of your weak acid? Okay. Sure, the last part about what you need to know, or this slide? Sure. So we have our buffer, and it's got acetic acid and the acetate ion, right? We add in a little bit of acid. That's the H3O plus. That acid is going to interact with the conjugate base. Because remember, an acid will donate a hydrogen. So it donates a hydrogen to the conjugate base to make more of your weak acid, the acetic acid. That's what happens when you add a little bit of acid to a buffer. So your equilibrium shifts and you make more of the acetic acid. You have a little bit less of the conjugate base. But again, your pH is still maintained. Other questions, or can we move on? All right, I'm going to guess that we can move on. So this slide summarizes kind of what I was saying on both of those slides. So I'm not going to go back through it, but just remember that the pH is always maintained when you're just adding small amounts of acid or base to a buffer. We can calculate the pH of a buffer. So just like any other solution, you can always calculate how much hydronium ion you have, which is the H3O plus. And when you do that, you get this ratio as part of your answer, which is the weak acid over the conjugate base. So does everybody see how that math is kind of worked out, where you're solving for the H3O plus, and when you rearrange, you end up getting this ratio of acid to conjugate base. I can go through the math if you need me to. Okay. So here's how it's solved. And we're actually going to do a problem similar to this. So Olga, if you can hold on for a second, you'll get to see a full problem solved where we start with the acid dissociation expression and move through to find the pH. Okay. So you will need to do this for the exam. So you'll need to write the acid dissociation expression, which was something that we did earlier on in chapter 11. And then you'll need to be able to rearrange it to solve for the hydronium ion concentration. And I'll show you how to do that. So this is a learning check that I went over in the YouTube video. And then I have another problem for you to try on your own. So I'll walk through this one, and then you can do the next one. Here, we've got acetic acid and water. And we have a buffer that we're preparing with 1 molar acetic acid and 1 molar acetate ion. We have to figure out the pH. What we have here is the equation, the partial dissociation of acetic acid in water. We need to write that Ka. As a refresher, what you're doing is you're writing the concentration of the products over the concentration of the reactants. We don't include anything that has a constant concentration. So that means any liquid, pure liquid like water, not included in the Ka expression, okay? So for this one, the products we have are the acetate ion and the hydronium ion. The only reactant we have is the acid. That's our acid dissociation expression. Is everybody with me so far? Now what we have to do is solve for the concentration of hydronium. The first thing we're going to do is multiply both sides So multiply by the concentration of the acid. And that will get it out of the denominator. Oops. Now we have to get rid of that acetate ion. So we're going to divide by that concentration. That's how you rearrange the equation. We can put in numbers to this and figure out the concentration of hydronium. So let's do that. The Ka we're given. There's no units for the Ka. And we're multiplying that by the ratio of, we've got 1 molar over 1 molar. So that's pretty simple. So that means our concentration is 1.8 times 10 to the minus 5 molar. But we're not done yet. The question is asking for the pH. All we have is the hydronium concentration. The pH is equal to the negative log of the hydronium concentration. I would encourage you to try that in your calculator right now, just to make sure that you can use the log function. Make sure you can use your calculator, you don't have any problems. So let me know what you get. You can put it in the chat. So remember, for pH, you have to have, for sig figs, the number of decimal places. So after the decimal, the number of decimal places that you have after the decimal is equal to the number of sig figs in the concentration. So you should get something like 4.72 or 74 or something like that. 77. But you need 2 decimal places here. I think it was 74. Yeah. So yeah, pH is a little bit funky when it comes to the sig figs. The number of decimal places that you have, as in the number of places after the decimal, should be equal to the number of sig figs in the hydronium concentration. We only have 2 sig figs, 1.8, so we need to have 2 decimal places. So that's our final answer, 4.74. Jordan, you had a hand raised. What's your question? Okay, great. Alrighty. Do we have other questions, or are you ready to tackle one on your own? Alright. So here, I'm not giving you the equation. I want you to write out the dissociation equation and then the expression. So you have hydrofluoric acid, HF, and it partially dissociates. What is the pH of a buffer prepared with 2 molar HF and 3 molar F minus? So you're going to go through the same thing. The only difference here is you need to write out that equation for how the hydrofluoric acid interacts with the water. And this is kind of hearkening back to what we did earlier in chapter 11. So I'll give you 5 minutes, After a couple of minutes, I may write up the equation just so that if you're stuck, you have something to go with. But I'll give you 5 minutes total to work on the problem. Okay, so I know that at least one person is stuck on the equation. If there's one, then that means probably more. So I'll help you out. So this is the dissociation equation. And then I will also put up the Ka. This is the acid dissociation expression. I'll give a couple more minutes to see that we have one answer. But I'll give a couple more minutes, and then I'll check back in and solve the rest of it. Oh, no problem. I'm glad you said something. Otherwise, you would have just stayed stuck. So you probably helped some other folks too. Thanks for speaking up, Olga. I'm going to start solving the problem now. So if you're still working, that's okay. So we have to rearrange this equation first to get to what the hydronium concentration is equal to. We add in the numbers. And we get a hydronium concentration of 2.3 times 10 to the minus 4 molar. Next, you have to figure out the pH. And that's the negative log of the hydronium concentration. Your calculator should say something like 3.6383 or something like that. But we only need 2 decimal places because we have 2 sig figs. So you should get 3.64 for the pH. So I saw we got some answers that were close, and it may just be a math thing. But how did that work out for everybody else? Did you just need more time? Do you have questions? Let me know. Yeah, so in an exam situation, if you got 3.63, you probably would have been able to choose the right answer. So that's just a rounding error. What's your question? So for the math, when it always works out to where it's the acid, the concentration of the acid, over the concentration of the conjugate base. So the concentration of the acid is 2 molar and the conjugate base is 3 molar. When you work out the math for rearranging everything to solve for the hydronium, it's always going to be in the same format. And I can write that out for you. So if the math makes you a little crazy, you can remember that. So you don't have to do the math every time. Does that help? No problem. So yes, I would definitely recommend practicing that. It will likely be part of your mastering chemistry homework. So if you have questions on that, you can definitely stop by office hours tomorrow and we can do some more practice. But in the interest of time, oh yeah, go ahead. One more question. So for the Ka value, you may be able to find that because there's a table in this chapter that has the Kas for strong and weak acids, and it also has the Kb for strong bases and weak bases. So if it's one of those in the table, you can find it. In terms of the pH, you need to know the concentrations of both the acid and the conjugate base, otherwise you can't figure it out. So unless they give you some other information about it, you can't figure it out. You're welcome. Alrighty. So we did some calculations with the Ka. We looked at the ratio of the weak acid to the conjugate base. And when you add small amounts of either acid or base, you're only slightly changing that ratio, so your pH is going to be maintained. However, there is such a thing as adding a large enough amount of acid or base where you can exceed what's called the buffering capacity. That means you have wrecked your buffer, you've added so much acid or so much base that it can't maintain. So you're going to see the drastic change in pH. Does everybody understand that? There is such a thing as too much acid or base for a buffer. When it comes to using a buffer and making a buffer in a lab situation, the buffer you choose is really dependent upon the pH you're trying to maintain. So different acid-base conjugate pairs maintain different pHs better just based on what their pH is when you dissolve these things in water. One of the very common buffers that you'll see in biology labs, biochemistry labs, cell biology, is phosphate buffers. This is the Ka for the acid. And you can rearrange the Ka, the acid dissociation expression, just like we did with acetic acid and hydrofluoric acid, to solve for the hydronium concentration. So that's all that's shown here. And again, we're looking at this ratio of weak acid over conjugate base. when we look at this ratio and we play around with some numbers, let's say that in the first scenario we've got 1 molar acid and 0.1 molar of the base. That's a ratio of 10 to 1. So we've got a lot more acid than we do base. Your pH is going to be lower. It's going to be more acidic, which makes sense, right? You've got more acid, so you have more hydronium in solution. If they're equal, then you're going to be closer to neutral, because you've got about equal amounts of hydronium and hydroxide. However, if you have more of the conjugate base than you do the acid, then it's going to be more basic. So understanding this concept that when you make a buffer, if you have more acid, it's going to have a lower pH. It's going to be more acidic. Versus if you have more of your conjugate base, it's going to be more basic. Does that concept make sense? We're going to do some practice problems, and I have a problem on this specific topic. So if you're like, I think I get it, we'll test you and make sure. That's coming up towards the end. Now we're going to talk about buffers in blood plasma. You definitely want to listen up here, because there will very likely be questions on your exam about this and how the buffer works in our blood. So normal pH for your blood is 7.35 to 7.45. Very, very tightly controlled. If your pH dips below 6.0 or it raises above 8, your cells can't function. So you may have cellular death, and it can be fatal. In our cells, carbon dioxide is made constantly. It's a product of cellular metabolism. We use our lungs to breathe in and breathe out, and when we breathe out, we're breathing out some of that carbon dioxide. But some of it dissolves in those body fluids like your plasma, the blood plasma, and saliva. And you form carbonic acid, which is H2CO3. It's a weak acid, and so it gives you a conjugate base and hydronium. And I'll write out this equation for you. I want you to get comfortable with writing these equations. So that's the equation. We said that for a buffer, you have to have large amounts of acid and conjugate base. We covered the acid part. The carbon dioxide dissolves in your blood and other body fluids to create carbonic acid. But that's not going to give us very much of the conjugate base. That's where the kidneys come in. The kidneys will also supply more of the conjugate base, which is the bicarbonate anion. So we said carbon dioxide is a product of cellular metabolism. It gets dissolved into our fluids. We make a weak acid. That weak acid makes a conjugate base and hydronium ions, and the kidneys also add some conjugate base. You should be able to, with this equation, understand what happens when you have excess acid and when you have excess base. When you have excess acid entering the body, that's going to interact with the conjugate base, and you're going to form more of your carbonic acid. If you have excess base, then that will interact with the acid and you'll make more conjugate base. Are you with me so far? Okay. So we said the pH of blood plasma is somewhere between 7.35 and 7.45. That means the ratio of acid to conjugate base needs to be about 1 to 10. It's a little bit on the basic side, just slightly basic. The concentrations of these things in our blood are here, 0.0024 molar and 0.024 molar. And that works out if you solve it like we did the other two problems, where you solve for the hydronium concentration, which that's what this is, and use that to solve for the pH. You get about 7.37, so that's about 7.4. So this is what's actually going on in your blood right now. The amount of carbonic acid that is in your blood is very closely associated with the partial pressure of carbon dioxide. Carbon dioxide is in our environment, right? It's in your house, it's in your dorm, it's in your classroom, it's in the atmosphere from industrial processes and from just trees and plants living, right? So we're around carbon dioxide all the time. If you're in a place where you have elevated carbon dioxide, like in an office building or an academic building or something like that, where there isn't a whole lot of airflow or exchange between outdoors and inside, you could have more carbon dioxide dissolved in your blood. And that would increase the amount of acid you have. In turn, that lowers the pH of your blood. So it may not be that drastic, being in a building for 3 hours or something like that. But it does have an effect. Having higher carbon dioxide in your atmosphere around you can have some effects, like it can make you lethargic, it can affect your academic performance, things of that nature. If it's very extreme, you can experience a condition called acidosis. If you have too little carbon dioxide, you have a similar thing where that level will lead to a higher blood pH, which means that you've got a decrease in the carbonic acid. And that's called alkalosis. This table has some examples of respiratory acidosis and metabolic acidosis. So those are two different things, respiratory versus metabolic. Metabolic means that it's something that's caused by your body. It's your metabolism doing something that's causing an increase or decrease in carbon dioxide in your blood. Respiratory acidosis is something that is caused by your environment. And it's the same thing with alkalosis. Environment for respiratory versus your body is doing something, your metabolism is sick, for metabolic alkalosis. So you don't need to know all of these different symptoms and causes and stuff like that, but you should be familiar with what acidosis is and what alkalosis is, and how how it relates to the pH of your blood, increased acid, decreased conjugate base, those kinds of things. So it's a lot of information, but hopefully it's a little bit interesting if you're interested in the health sciences. So that's blood. That's how buffering works in the blood. Are there any questions about that? This is the last part of 11.8, and we're going to move on to exam 4 review if we're good. So let me know if you're ready for exam 4 review. All right. So as usual, I've got some questions. They're all multiple choice, just like you'll see on the exam. I'll give you a few minutes to work on them, and then I'll go through them. So like I said, I've got about, let's see, how many do I have here? I think we have 17 questions, 17 multiple choice questions. I'll give you a few minutes, then we'll go over what's on the slide, and we'll press forward. So I'll check in about 5 minutes just to see where you are with these 3 questions. If you don't finish, that's okay. We don't have all the time in the world, so I can't give you 30 minutes each time we work on questions. But hopefully you'll at least see, ooh, I don't remember that at all. Or, got stuck here, and that's the goal. So work for about 5 minutes, and then I will come in, see where you are, and start answering questions. If you get stuck, let me know. You can write it in the chat, and I will try to help you get unstuck. I'll start going over these. So number 1, when potassium chloride dissolves in water, we've got several options that talk about the ions and how they interact with each other or within the crystal. I'll tell you that the answer is E. And I'll just explain how something dissolves in water. So when you have potassium chloride or any ionic compound, you're going to have positive ions and negative ions. Water has some lone pairs on that oxygen, which makes it partially negative, and the hydrogens are partially positive. So water is a polar molecule. In order for something to dissolve in water, the water needs to interrupt the interactions within the compound itself. So we've got to choose one that talks about how the water interacts with the ions, either the potassium or the chlorine. And the only one that does that correctly is E, where the potassium ions are attracted to the partially negative oxygen atoms of the water molecule. What about number 2? Did anyone get to number 2? Or do we need a refresher on that one? Okay. So for number 2, you have to remember that for the charge, so aluminum, the ion is 3+. That means that you make 3 equivalents for every 1 mole of aluminum ions. We're given the number of grams of aluminum. We have to first figure out how many moles. Then we use the conversion factor to figure out how many equivalents. So it should be A. So C is tricky because if you just took the 5 grams and multiplied by 3, you'd get 15. But you have to realize 5 grams, you need to change that to moles. All right. What about number 3? This is a solubility question. So we've got the solubility of potassium iodide is 50 grams in 100 grams of water at 20 degrees Celsius. We've got 110 grams added to 200 grams of water. And we're asked what's going to happen. Well, let's just go through these because we can eliminate a lot. The solution will start boiling. Well, that doesn't even make any sense. You're not going to add something to a solution to cause it to boil. All of the potassium iodide will dissolve and the solution will be unsaturated. Those say the same thing. And since the option of B and C is not an option, that means it can't be B or C. The solution will freeze. Again, you're not going to add an ionic compound and cause a solution to freeze. So just by the process of elimination, you can get to E. But if we look at the numbers, 110 grams over 200, that is greater than the solubility. So that means we're going to form a saturated solution. How did we do on those? Any questions? Alrighty, we'll move on. So the next few, we've got some solubility rules questions, and then we've got a concentration question. So I'll give you another 5 minutes. You can put in your answers as you get them, or you can just wait. It's totally up to you. But I'll give you 5 minutes, and then I'll start solving them. I'm going to start going through these, starting with number 4. Which one of the following compounds will be insoluble in water? So you need to use the table that I put up here, table 9.7, and that tells you the rules for ionic compounds in water. For this, all you really need to do is go through each compound one by one and say, okay, is this soluble or insoluble? For A, we've got lithium nitrate. Lithium is one of those ions that if you see an ionic compound, it's very likely soluble. Same thing with nitrates. So that one's soluble. Potassium is another ion where if you see a compound with potassium, it's going to be soluble. Chlorides are also soluble, with some exceptions. Magnesium is not an exception, so that means magnesium chloride should also be soluble. Lead 2 sulfide. Any ionic compound that doesn't have at least one of the ions mentioned in this chart, it's probably going to be insoluble. We don't see sulfides on this chart, so we're going to say that one is very likely insoluble. And just for completion's sake, for E, we've got sodium hydroxide. We see the sodium ion. Most things with sodium are going to be soluble, so that leaves us with D. Number 5 is a similar question, only here we're looking at a double replacement reaction. When you mix ammonium chloride and potassium nitrate, what do you get? So in order for a precipitate to form, you need to form a solid, something that is not soluble. So if we've got the ammonium ion, chlorine ion, potassium, and nitrate, we're going to pair up these two and we're also going to pair up these two. So that's a double replacement where you swap ions. Now the question is, are these two compounds soluble or insoluble? Well, the first compound, ammonium nitrate, it's got ammonium and nitrate. If you see those ions, it's likely going to be soluble. We've got potassium chloride. If you see a potassium ion or the chloride ion, again, likely soluble. So that means when you mix those, you actually don't have a precipitate form at all. Are there questions on that one? So don't forget to use the solubility rules once you figure out what your products are. So we have to take solubility into consideration, because if we've just got ions floating around, so these two compounds are soluble. That means you're just going to have all the same ions floating around in solution. A precipitate that means that you have a solid formed as a product. In order for something to be a solid, it has to be insoluble. So you have to use the solubility rules to figure out if you're making something insoluble. I saw a hand raised. Is there still another question? Yeah, go for it. They can mix, but the question is, will you form a precipitate? And the answer is no, because making a precipitate means that one of these two has to be insoluble, and they're both soluble. Other questions about this? Yes, if one of the products was insoluble, then you would form a precipitate. So an example of that would be if we were to mix barium chloride and lead 2 nitrate. Then you would form barium nitrate and lead 2 chloride. Lead 2 chloride is insoluble, so it would be a solid, and a precipitate would form. Yes, another question? Yes, you will not need to memorize it. You're welcome. So does that clear it up a little bit more about whether a precipitate will form or not? It's not just what will the what will the two solutions be? You need to be forming a solid. That's what a precipitate is. Okay. All right. And this last one I will do in a different color. What is the mass by volume percent of a solution prepared from 50 grams of sodium chloride and 2.5 liters of water? The trick here is to know that for mass by volume percent, your volume needs to be in milliliters. So it's usually in grams per milliliter. .5 liters of water, that's equal to 2,500 milliliters. So you should get C. Again, this is the trick here. The volume has to be in milliliters. Let me know if you have questions or if you're ready to move on. Okay. Let's do it. Here we've got two math ones, and number 8 might be, it's not a hard problem, but we haven't done one like it. So I wanted to put it up there just in case you see something like it on the exam. I will give you 5 minutes, and then I'll check back in. I'm going to get started solving number 7, and then we can talk about number 8. Number 7 is a straight up molarity question. You got to figure out the molarity of a solution that contains 17 grams of ammonia in 0.50 liters of solution. Whoops. The key here is we have 17 grams. Molarity is moles per liter. So we need to get to moles of ammonia. We need the molar mass to do that. I abbreviate molar mass MM. To calculate that, you need to know what nitrogen is, which is 14.01 grams. And then there are 3 hydrogens, and they're each 1.01 grams per mole. Now we can figure out how many moles. We've got 17 grams of ammonia. We use a conversion factor, which comes from our molar mass. Your calculator is going to tell you something like 0.997 moles. But with sig figs, that's 1.0. For molarity, you take the number of moles and divide by the number of liters. So we've got 1 mole over 0.50 liters. That gives us 2 molar. That's A. Questions on that one, or are we good? I'll do number 8 in a different color. So with 8, we've got a balanced equation, and we're asked how many milliliters of 0.234 molar potassium chloride solution will react completely with 25 milliliters of 0.168 molar silver nitrate solution. The key here is understanding that with this balanced equation, the ratio of moles is 1 mole of potassium chloride is required to fully react with 1 mole of the silver nitrate. So however many moles of silver nitrate we have, that's how many moles of potassium chloride we need. If you take molarity and you multiply by the volume in liters, that gives you the number of moles. And if we're saying the moles of potassium nitrate have to equal the moles of the potassium chloride, then we're saying the molarity times the volume, which remember, we have to use liters here. So 25 milliliters is 0.025 liters. That's our moles of silver nitrate. That's going to be equal to the molarity of the KCl, the potassium chloride, times some volume in liters. That's what we're trying to figure out. To do that, you're going to divide both sides by 0.234. So you should get D. Does that concept make sense? I know it may have tripped you up a little bit, but let me know how question 8 works for you. So you can use a conversion factor to get from milliliters to liters. You can also use one to get from the number of moles of silver nitrate to moles of potassium chloride. For me, I think this way makes the most sense. But if you did it a different way that makes sense to you, go for the gold. The concept is still the same. How you work out the math may be a little bit different. Yes, what's your question? So it's similar to that, but it's not a dilution. What we're saying when we're doing a dilution in general, what we're saying is the molarity times the volume is equal to the number of moles. And what we're saying here is this is true for these two things. The number of moles of silver nitrate is going to equal the same number of moles of potassium chloride. So it's similar, but I didn't write that equation because it's not exactly the same thing. If you have more questions, we can go over it again. Sure. Okay. So it could just be part of how you did the math in terms of the 1,000 milliliters versus the 25 milliliters. But it sounds like you should be able to get the right answer from that. Other questions? So again, the main goal is if you understand that you have an equation here and the number of moles is going to be the same, there's a couple of different ways you can do the math. To my brain, this makes the most sense. If it makes more sense with the conversion factors to you, then that's fine too. And if you want to go over that more specifically, you can come on to office hours and we can throw it up on the board and dissect it there. Now let's move on so we can get through the rest of these. I'll give you another 5 minutes for this. For number 10, I'm going to give you a little bit more information because you'll get this on the exam as well. So that should help you for number 10. I'll give you about 5 minutes and check back in. Let's get started with number 9. A red blood cell will undergo hemolysis in, and you have to choose which buffer solution or water, essentially. Hemolysis, that means that the cell is going to swell and burst. In that kind of a scenario, there's going to be a lot of water flowing into the red blood cell. So we're looking for a hypotonic solution. Those two percentages that I gave you before you're going to want to know those two cold for what IV fluid is, so you can make the comparison. We're looking for a hypotonic solution, and the only one is E, water. We good on number 9? Number 10. We've got half a mole of sodium phosphate, which is a strong electrolyte, and it's added to 1 kilogram of water. The freezing point of the solution will be... We did an example of this, and we also did boiling point elevation. The first thing you have to do is figure out how many equivalents per mole are in this sodium phosphate. When you add this to water, you're going to make sodium ions and phosphate ions. The number of ions that you make is 4, which means you have 4 equivalents for every 1 mole of your substance. From here, you can figure out how many equivalents you have in half a mole. And then use the freezing point depression information that I gave you. So for every 1 equivalent, you have a 1.86 degrees Celsius drop in your temperature. So we're calculating the change in temperature right now. That gives you 3.7 degrees Celsius. But that's the change in temperature, not the freezing point. The freezing point, you have to take the freezing point of water, which is 0 degrees, and subtract your delta T. So your answer should be E, negative 3.7 degrees Celsius. Questions? Or are we ready for number 11? All right, number 11. Which of the following is the strongest acid? The strongest acid is going to have the largest Ka value. So you have to look at the Kas for all of these and figure out which one is the biggest. C has the biggest value, so it is the strongest acid out of the 4 options. But they're all weak. It's the strongest of the weak acids. The flip side of that concept is the weakest acid has the smallest Ka. So how we feel about these questions so far? Are we doing good so far? Shaking off some of the cobwebs from last week? Hopefully we're being enlightened a little bit, perhaps. How are we doing so far? Good. As usual, all this will be posted And you'll have the PDF so you can go back over these questions at your leisure. So we're almost done. Now we're doing some calculations with pH. For the interest of time, I'm going to kind of walk through these a little bit for you. Feel free to work ahead of me, but I want to make sure that we get through all of these and you can ask your questions if you have questions. All of these are kind of related in terms of manipulating pH and the dissociation of water. So number 12, what is the hydroxide concentration in a solution that has a hydronium concentration of 1 times 10 to the minus 6 molar? You have to use the kW here. You'll be provided with that equation. You won't have to memorize it. To figure out the OH concentration, you divide both sides by hydronium. Then you substitute in your numbers. The kW is 1 times 10 to the minus 14. And we're given the molarity of the hydronium in the problem. If you know how to work your exponents, you don't need to touch a calculator. Otherwise, you can put it into your calculator. What you should get is C. Questions on 12? All right, I'm going to keep trucking along. You let me know. Stop me if you have questions. What is the pH of a solution with hydronium concentration of 3 times 10 to the minus 3 molar? This one is pretty straightforward. You substitute in your hydronium concentration. And don't forget that negative sign. If you forget the negative sign, you'll get a negative answer. And that's wrong. Your calculator should tell you something like this, which you need to know. With sig figs, you need 2 decimal places. And the answer is E. Notice how there's negative 2.52 as an answer. If you don't include the negative sign in front of the log, you'll get negative 2.52. So you need to be careful here. Now we'll go on to number 14. Again, stop me if you have questions. What is the pH of a solution with hydroxide concentration of 1 times 10 to the minus 4 molar? We're combining what we did kind of in 12 and in 13 to get the answer for 14. You first have to use the kW to get to the concentration of hydronium, because the pH, that's what we need. Now that we have the hydronium concentration, we can stick that into our equation for the pH. You should get letter B. So this is all about manipulating the KW and knowing how to use the pH equation. Questions, or are we ready to move on? So this is the last set of 3 questions that I have for you. Yes, the KW is always equal to that at 25 degrees Celsius. We're not putting that in every single problem, but that's the only value that you have. The KW changes with the temperature change, but don't worry about that. So number 15, we're trying to find the hydroxide concentration of a solution with a pH of 8.34. We have to work backwards. We can get to the concentration of hydronium from the pH. And that's the equation we have to use. Again, don't forget that negative sign because it makes a big, big difference in your answer. So that's our hydronium concentration. Notice how that's an answer. Don't stop here. The question is asking for hydroxide. So you again have to go to your KW equation. Oops, that should not be minus 19. Should be minus 9. And once you do that division, you should get 2.2 times 10 to the minus 6 molar, which is D. And if we think about pH, that makes sense. A pH of 8.34 is going to be basic. So it's going to have a concentration of hydroxide that is greater than 1 times 10 to the minus 7 molar. That's another way you can kind of check yourself in your calculator answer to make sure that you're on the right track. And if you just think about that, you can rule out A, B, and C as answers before you even touch your calculator. So those are just some test taking tips to remind you of when you're taking your exam. It's not always, what is the exact answer, but what you know the answer can't be. Don't forget that. Number 16, which of the following could be a buffer? Well, a buffer has to contain a weak acid plus a salt of the conjugate base. So A, we see a weak acid, but water is not a conjugate base. In B, we see a salt plus a weak acid, but we're not making the correct conjugate base. Cl minus is different from F minus, so that can't be a buffer. In C, we've only got a salt, so that can't be right either. In D, mixing a salt with water is not going to give us a buffer because we have no weak acid. In E, however, you have the weak acid, the hydrofluoric acid, plus its salt, sodium fluoride. It's the only one that it can be. And the final question, which solution has the highest pH? And we're looking at buffers and the ratio of weak acid to conjugate base. Remember, we did this. Just the generic equation for the amount of hydronium ions in solution. That's the concentration. So if you have more acid, then you're going to have a lower pH, which is more acidic. If you have more of the conjugate base, you're going to have a higher pH. What we're looking for is the one with the highest pH. So it has to have the most conjugate base in reference to the amount of weak acid. The only one that fits the bill is C. We've got 0.01 molar acetic acid and 0.1 molar sodium acetate. Any questions here? So when I did it on my calculator, I also got only 2, but the closest answer is 2.2. So I don't know if that's a typo in the sample questions, or if it's a matter of not having enough significant figures on the calculator. But I saw the same thing. But the only answer that it can be is D. Other questions? Oh yeah, no problem. It happens sometimes. So the last thing that I have for you is reminders. And of course, that's when my son decides that he wants to make an appearance on our video. But it's okay. It's the last one. So you have your Master in Chemistry, which is due on Sunday. Remember, I changed it. It was supposed to be due last Sunday, but we didn't finish all of Chapter 11. And I'm not going to do that to you. So you have until this coming Sunday, and you can stop by office hours this week, 2 to 4 p.m., if you have questions. You have an exam this week, which is going to be available tomorrow, and it will disappear Friday, November 20th. So please make sure you take it. You will also have a final exam on December 8th. Yes, Jordan, what's your question? Yeah, so next week is Thanksgiving and nobody goes to class. So you can go home early if you would like. Um, because a Tuesday morning class, most people are not going to attend. That's the last class period. Yeah. So this is the last real class period that we have before your final. What we can do, and what I was going to bring up, is that we can have some office hours the week before finals week. So I was going to post that in Blackboard to see when you all would like. If the Wednesday time slot works, since nobody has class anymore, we can just stick with that. But I was going to have office hours and also post a little bit of a review for you to practice on before your final on December 8th. Does that help? Right. As long as you start it by then, you should be good. You're welcome. Okay, so if you work during the final exam, see if you can move that. Otherwise, talk to me, send me a message through course messages, and we'll work out an alternative time. But you have to do that with me by the end of this week. So if you know your work schedule, which you likely do, let me know, and we'll work out an alternative time for you to take the exam. Yes. What's your question? Yes. So the final exam is just going to be, um, it's going to be pretty much the pool of questions in terms of the multiple choice questions that you've had all along. So you may see questions that you've already seen before on exam 1 or exam 3, but you may also see some that you didn't have before. And it will all be in respondus. The final exam it's 20 or 25%. I can't remember which, but it's a significant portion of your grade. So you definitely want to study and you want to do your best. Next week, no class, no office hours. Happy Thanksgiving. Travel safe if you're traveling. Wear your mask, wash your hands, all those things. Please, please, please be safe because the the virus is starting to explode. Okay. Oh, thank you, Olga. So please be safe this holiday season. Enjoy your family, enjoy your friends. Um, if you need anything in between now and finals, I'm here. I'll check my messages. So if you need something, just shoot me a message on Blackboard and I will do my best to help you. But again, we still have office hours tomorrow. So if you need time before that, if you have class or something in the 2 to 4 time slot, shoot me a message and we can set something up beforehand in the 12 to 2. That's when I do the individual meetings. So let me know. If you need anything, I'm here for you. I want y'all to do well. It's been a pleasure being your instructor. I don't want to see any of you again in Chem 104, but if I do, that's all right. Have a good one, you guys. I don't have anything else for you, but you're free to go.